start immediately the morning session. It's my pleasure to introduce George Andrews, who's going to speak on a refinement of the Alladi-Schur Theorem.
So rather than thanking all the organizers, as the senior organizer and therefore the least useful organizer, I want to thank a number of people who have made this conference such a success. In particular, Frank and Cindy Garvin and Margaret have really been the people behind the scenes who have done so much, and I am truly grateful to them, and I know that we all are. And in addition, of course, the staff connected with the University of Florida Mathematics Department has been extremely helpful. I'm also grateful to all of you for coming to and attending this conference. The diversity of talks has made this one of the truly exciting conferences that I have been fortunate enough to attend in many years. And I'm grateful to all of you, and I'm especially grateful to my good and old friend Krishna Alladi, who provided the marvelous excuse for having this grand conference. When Frank first suggested the conference to celebrate his 60th birthday, I said, that's not possible. He's always been 48. But Frank convinced me that he really was 60, and so we have had this glorious event. So thank you all. The title of my talk this morning is A Refinement of the Alladi-Schur Theorem. So I've been warned that I cannot possibly go over time, so the first part of it will perhaps go a little quickly, but fortunately for me, a number of people have talked about the items that I am going to begin with in order to set up the discussion of this theorem and why I think it is a significant result. So we start with the famous Rogers-Ramanujan identity, as you see it pictured here on the screen, both written out in extenso and then in the standard shorthand notation of classic Q series. Of course, that is the generating function version of this theorem, and it has an interpretation in terms of the classical theory of partitions, where the series generates partitions with difference at least 2 between parts, and the infinite product generates partitions into parts congruent to 1 and 4 mod 5, so that, for example, when n equals 13, here is the first class of partitions, and at the bottom of the screen you see the second class, and these are indeed equinumerous. And then, just to make clear, there is this second Rogers-Ramanujan identity, very similar to the first. The change in the series is only that in the exponent of Q in the series, n squared has been replaced by n squared plus n, and in the infinite products, 1 and 4 have been replaced by 2 and 3. The only change in the partition aspect is that now 1s are excluded when you look at partitions with difference at least 2 between parts, and instead of 1 and 4 mod 5, you have parts congruent to 2 and 3 mod 5. And the example the previous example now has fewer partitions because we've thrown out at the top line all those with 1s. At the bottom line, things are of course completely different because none of the summands will be the same. Going even much farther back in history, really the prototype of all theorems of this nature goes back to Euler. The number of partitions of n into odd parts equals the number of partitions of n into distinct parts. And as a result of this, one can look at an obvious, since all mathematics is linear, one can observe that Euler's theorem looks at partitions where the difference between parts is at least 1, and odd numbers are, of course, congruence classes 1 and 3 mod 4. The first Rogers-Ramanujan identity has difference 2, and the congruence classes are 1 and 4 mod 5. So one would hope that this might be the beginning of an infinite family of theorems. And, of course, one starts to write such a theorem of this nature down, and your heart rate increases as you move down the slide here, and everything goes fine. And now it is really beating fast, and all of a sudden it falls off a cliff. So I'm reasonably sure that prior to 1926, Schur is the one who looked at this and said, well, obviously there's a ringer in the left-hand column. Which one seems most reasonable to throw out? And the 6 plus 3 is what he threw out. And he came up with, and eventually proved, this theorem. Number of partitions of n into parts congruent to 1 or 5 mod 6 equals the number of partitions of n into parts that are distinct non-multiples of 3, and that equals the number of partitions of n into parts that differ by at least 3 and by greater than 3 for multiples of 3, thus throwing out that nasty 6 plus 3 that was ruining the column of partitions that I showed you originally. So the example that I created, that's caused my heart to race somewhat fast till I realized I'd omitted 10 plus 2 plus 1 in the middle there. So the first two lines are as easy to prove as Euler's original theorem. They are just manipulations of infinite products. The real challenge for Schur was to identify these partitions. But this indeed is the natural way that one would discover Schur's theorem. And as I recall when I was a graduate student, Rademacher, in referring to this theorem, gave some history of it in that he had suggested to Gleisberg that perhaps there might be an arithmetic proof. And in searching for and finding effectively a proof that did not use generating functions, as Schur did, Gleisberg found a refinement of Schur's theorem, where now you look for distinct non-multiples of 3, but you count not only the number being partitioned, but also exactly how many parts there are. So the number partitioned is n, the number of parts is m, and you have a slightly strange count of the partitions involved in that. You count, when you are counting the difference at least 3, you count the parts as you would just count them one by one, with the added condition that you count multiples of 3 twice. And so in that way, you obtain this identity of these functions. And the proof of it is effectively, this is not Gleisberg's proof, but it makes clear, at least to me, what's going on. Basically, you look at a restricted generating function where this d sub n are these types of partitions, except that the largest part is at most n, and then it is an easy matter to show that this recurrence relation holds along with these first couple of values. You can then determine all of these polynomials, and basically the argument behind this recurrence is that you look at whether or not the partitions contain this largest part, capital N. If they do not, they're all enumerated by this first sum n. If they do contain capital N, then indeed you have to have to make a count of either 1 or 2, depending on whether or not n is a multiple of 3, and you have to account for whether the difference is 3 or 4, depending on whether, again, whether n is divisible by 3. And then it is possible to prove that this functional equation holds between these polynomials. And if you let n tend to infinity, then an iteration of the infinite functional equation reveals that this is the generating function for partitions where the distinct non-multiples of 3. So, how does this get to be involved with Alladi? Well, probably there's no one on Earth who has studied more extensively Schur's theorem. He, along with Basil Gordon, developed a method of weighted words to provide new insight into Schur's theorem. Indeed, they found previously there had been one variation of Schur, an equivalent formulation. He and Basil Gordon found 4 more and developed this beautiful method. I have only one criticism of it, and that is that when the experts on this make presentations, they often use colors in weighting the words, and usually blue and red will be the primary color, and then they use green as the secondary. Everybody knows if red and blue are the primary colors, purple is the secondary. Other than that, it's great stuff. However, in addition to the work on weighted words, Alladi was the first to notice that there's another infinite product floating around that is identical with the generating function that Schur originally dealt with. And so this top line is the generating function for partitions in which there are odd parts that appear at most twice. And so this is a further equivalent set of partitions, equivalent in the sense that the number of partitions of n is the same as the 3 formulations that we have originally of Schur's theorem. So the question, as in the light of the fact that I want to make sure that everybody gets to their flight, I will probably have little time to explain why I would undertake this study. But basically, in case I don't get to say too much, there's a conjecture that has come from 2 graduate students at Rutgers University that I've been working on unsuccessfully for more than a year. And so anytime you start to really flounder on something, you say, well, maybe there's something that sort of looks like this that would be easier to handle. And this Alladi's version of Schur's theorem looks like some of these conjectures, and so I wanted to see what could be done in the way of refining this and finding new methods for proving this. So here is the central theorem that I want to talk about, and in some way I want to try to make the point that this is the Alladi's version of Schur's theorem is really much more central to Schur's theorem than the original formulation. So that is basically the thrust of the message, because I think that that observation may lead to understanding of the conjectures that are still so tantalizing. So the refinement goes as follows. It's precisely the same as Gleisberg's idea, only now we're going to count partitions into odd parts where no part is repeated more than twice. So we partition n, and there are n parts. And just as with Gleisberg, we make a weighted count now of partitions of n and n parts with the Schur conditions difference between parts at least 3, greater than 3 for multiples of 3. But now instead of counting multiples of 3 twice, we count the even numbers twice, and then this is the theorem. And as a prototypical example, there are the 3 partitions of 12 into 4 parts. First, odd parts with 4 parts with no odd part repeated more than twice. And down here, keep in mind we're doing a weighted count, so that these top 2, all parts being even, means that the count is 4. And here, 1 part being even, again, also means the count is 4. So the proof is somewhat more painful than the proof of Gleisberg's version of Schur, but it is in effect exactly the same idea. Namely, what one wants to do is to look at the generating function where all the parts are less than capital N, and now it is in effect the same functional equation, except now the exponent on t varies according to evenness and oddness rather than according to the multiple of 3. And so I won't, as I said, the details of the proof are rather painful, but an outline of it is not painful at all. Namely, you look at these 2, Fn and Gn, as linear combinations of these generating polynomials, and the idea is that these expressions are identically 0. In particular, then, if this line is identically 0, the same argument that was used effectively in the proof of Gleisberg's theorem, all one needs to do is to let n tend to infinity, and you have the functional equation for the infinite product generating function for partitions into odds that appear at most twice. And without really giving you the proof, but at least telling you what you need to do, these are the functional equations for the f and g that you need to prove, along with the fact that f1 and g1 equal 0. They are, once you know what's true, which is what your computer algebra package tells you, then the rest is quite straightforward. But what no one ever did until I really got hugely frustrated with the conjectures I was studying was to actually look at what the pure polynomials look like. And I want to show you every 6th value starting at E2. So E2, E8, E14, what happens is you don't need this sort of clever functional equation that you had before. The partial products of this infinite product are factors of this sequence of polynomials. So here you see the first factor. Here you see the first 2 factors. I wrote this in just because it's there, but this is basically 1 plus big O of q to the 5th. It's not what I want here, but here are the first 3 factors of the infinite product. And to make sure that you're absolutely convinced, here are the first 4 factors of E20. And so, as I say on this slide, thus we see and can prove that this E6n minus 4, I've set t equal to 1, is factors with the partial product and a further polynomial. And what I'm preparing as part of the contribution to this conference is the full details of this factorization. the point is that intrinsic in this sequence are these partial products. Of course, Schur would not conceivably have had any reason to observe this. First of all, it is immensely painful to compute these polynomials by hand, which is what you would have had to do, and going, say, up to E20, and then factoring it like this, when you don't expect this partition theorem, is not something that would be reasonable to expect of anyone. But the point I want to make here is that the Alladi-Schur theorem is embedded intrinsically in the sequence itself, whereas this is not true of Schur's original theorem. The factors that go into the products that Schur dealt with do not replicate themselves so that they become part of the intrinsic structure of this sequence of polynomials. And so I see I have 8 minutes here, which will allow me to say something about why I was interested in this version of Schur's theorem in the first place. So at the 2015 Joint Mathematics meetings in San Antonio, Jim Lepowski highlighted 6 conjectures by 2 then graduate students, Kanata and Russell, and he drew special attention to their 4th conjecture. So, in order to get you to the airport on time, don't read the second half of this. It's basically a bunch of difference conditions on partitions, but the idea is that partitions satisfying these difference conditions are equinumerous always with the partitions into these 4 residue classes modulo 9, and just to, you have to take this on faith, that there are 6 partitions of 11 of each type. Here are the ones subject to the difference conditions. Here are the ones in these 4 residue classes. More important and much more looking like Schur's theorem is, in effect, the analytic version. Namely, you have a sequence of polynomials defined by these recurrence relations, and the point is that as n tends to infinity, these polynomials converge to this appropriate infinite product. So, as often happens with me, I get sucked into a problem by knowing something that the posers of the conjecture didn't know, much as when I started on the borderline conjecture 25 years ago or more, and it's still open. Similarly here, I realized very quickly that you don't need to work with this infinite product with things in the denominator where the partial products are rational functions, as they would be here. You can, by a very simple manipulation of products, change it into an infinite product where the partial products are polynomials. And consequently, that's the way Schur's theorem is proved in all the examples that I've given you. And one hopes that one could do exactly the same thing here. So I rushed back to my hotel room in San Antonio and have been working ever since without success. So you have 2 polynomial sequences, these Q's and these partial products. Well, one of the things you can do to study this is to look at what happens when Q is equal to 1, because in the Schur case, you will get very simple, basically an example of a binomial theorem in one case, and if you look back to the Rogers-Ramanujan identities, you're dealing with identities related to Fibonacci numbers. So, the Q3n plus 1 seems to be the most amenable to treatment, and so if I set Q equal 1 and call a result G sub n, then the generating function for G sub n is this. So hopefully this polynomial in the denominator, after all it's only a cubic, should be something nice, and everything will be easy, just determining the Q analog. of course, the roots are this, and who knows anything about the cosine of 10 degrees? Once you ask your computer algebra package to solve this polynomial, you quickly know it. So I never went through solving a cubic before, but here come up the roots of the cubic, and stuffed in the middle of, even though these are real numbers, stuffed in the middle of the solution are square roots of -1, which of course somehow cancel themselves out, but there's nothing there that's really helpful. However, I then thought, what a clever fellow I am. On the other hand, the denominator can be done like that, and now you can expand this thing into a series of this nature, and you can get a relationship between the G and the P, which is this. And so obviously one should put the Q in there and the real product there and a Q binomial coefficient there, and then your computer algebra package will throw in a few other things and everything will work beautifully. And I came up with the following theorem, namely this. But unfortunately, the condition at the top of the page but obviously something neat is happening here, although at the next stage along everything falls apart, and I have no idea what is really happening there. So that is why I took up looking at the Alladi-Schur Theorem, because the infinite product that we're dealing with in this theorem, this finite product you see, is partitions where parts of certain residue classes appear at most twice. And that's why I backed up thinking, well, yes, there is Alladi's theorem, which should be somehow a prototype of what's going on here, and could one actually deal with this? And I have 50 seconds to tell you that the thing that goes wrong, or at least the limitations of my intellect have prevented me from finding any way to insert a second parameter in this, because all of the proofs that you have seen of Alladi-Schur's theorem or the Alladi-Schur theorem involve the appearance of a second parameter that makes things work well. And so that's where I am, and on this particularly depressing note, I thank you very much for your attention.
People have to go to the airport, so maybe take one question, or just maybe one question.
Is which published? So Kanata and Russell certainly have, I believe, in experimental math, either their paper has appeared or is going to appear. The original version of this generalization of Alladi-Schur will appear in a proceedings of a lattice path conference last summer, and the version that involves this actual intrinsic factorization is what I hope to contribute to the volume here. So that's reference our publication.
Okay, I think we'll quit for 4 minutes, 3 minutes before our next talk.